Go.
Hello everyone, my name is Daniel and I'll be doing another question under analysis model using Newton's second law. So today I'll be looking at weighing a fish in an elevator. So from this diagram, this is the scale, this is the fish, and this is us weighing the fish. So I'm just going to use Newton's second law to show all the forces acting on this fish. So if I set up my coordinates here, the force acting downwards is the gravity, so mass times acceleration due to gravity, and this will be our negative y-axis. The force acting upwards, that's trying to pull this fish upwards or at least holding it, is going to be the tension in this string. So the tension in the string, and this will be our positive y-axis. This is our positive x-axis to complete things. So as it's at rest, the forces acting on it will be the positive tension that is holding the fish and the scale, or that's holding the scale, and then the negative weight that is trying to bring it down due to gravity. And you'll notice that the whole body is at rest, so the sum of all these forces on the y-axis is going to be 0. So I'll write summation Fy is equals to 0. So I'll just equate this and bring this weight over there, and so T will be equals to mg. So at rest, the reading in the scale, which is the tension, is going to be the weight of the fish. So that's mg. So for the first question, we are going to show that the scale, the reading on the scale is going to be different from the normal weight on the fish if the elevator is going upwards or downwards. So I will do for upwards right here. So now let's say the elevator is going upwards. I can set up my axis again. This is mg and negative y. This is tension and positive y. This is x. This is x. Note that there is no forces acting on the x direction, so I could just write it as summation fx equals to 0. And now if it's going upward, if the scale is going upward, the fish is going to be having an acceleration, let's say ay. So we are going to call the acceleration of the fish be having upward ay. Now the sum of all the forces according to Newton's second law will be the mass of the fish multiplied by the acceleration of the fish. So we'll set up like how we did before. The sum of the forces acting on the fish is the tension plus the negative one equals to the mass of the fish times the acceleration of the fish. And this for the y direction. So I can write summation Fy is equals to T minus mg, and that's mass times acceleration in the y direction. Now the reading on the scale is going to be the tension, so I'll just write T equals to MAY plus mg, or rather mg plus MAY. And if the acceleration is positive, that's if the fish is going upwards, if the elevator is going upwards, you'll notice that the reading is going to be greater than the normal weight of the fish. This is the normal weight of the fish, and this will be the additional reading. Since this will be positive if it's going up, and the mass is also positive, the whole expression here will be bigger than just this one. So now I'm going to also like do some derive a formula for when the elevator is going downwards. So when it's going downwards, the sum of forces will be the tension and the weight pointing downwards, and that will be equal to the mass still times the acceleration. But when it's going downwards, since upwards is our positive axis, downwards is going to be our negative axis. So the acceleration then will have negative value. So I can write mass times negative acceleration, and that will just be negative mass times acceleration. And then I'll just set things up as T equals to, take this one there, mg minus mey. And so in the y direction, this will be our mass, our reading in the scale if the elevator is moving downwards. So you'll notice that this value is going to be smaller than mg. This value is smaller than mg because this is a number. If you are subtracting 1 from this other number, it's going to be smaller than this one. So that's all for this question. Okay, so for the B part, we are going to be evaluating scale readings for a 40 Newton fish if the elevator moves with an acceleration of positive or negative 2.0 meters per second squared. So I'm going to do, for positive 2.0 meters per second squared, AY equals to 2.0 meters per second squared. The elevator will be moving upwards, and for negative it will be moving downwards. So I'm going to do for when the elevator is moving upwards. From the formula we got before, it's going to be, the reading will be T equals to mg plus may. Now G is acceleration due to gravity and m is the mass of the fish. They didn't give the mass, so we are going to get the mass now as mg equals to 14 Newton, and m will be 14 Newton over 9.8 meters per second squared. So which is, I'll just get that value on the calculator, 4.08 kilogram. So the mass is 4.08 kilogram. Now I can get the tension, which will be the reading on the scale. So I'll say T equals to 4.08 kilogram. Or rather, I can just write the weight of the fish for this one. 14 Newton plus mass 4.08 kilogram multiplied by acceleration 2 meters per second squared. So this will be 14 Newton plus this times 2 Newton, and then we'll add the 2 to be 48.16 Newton. So you see the fish is going to weigh more when the elevator is moving upwards. The reading on the scale is going to be more when the elevator is moving upwards. So now we'll do for when it's moving downwards. When it's moving downwards, the acceleration will be negative 2.0 meters per second squared. And we can just set up equation from our first solvings to be T equals to mg minus may. So we've already calculated some parts. With our values, the weight of the fish mg is 14 Newton minus the mass, and you notice this minus is because of the negative acceleration here. So I don't need to make this ay minus 2 anymore. So the mass is going to be 4.08 kilogram multiplied by 2 meters per second squared, and that will be 14 Newton minus 8.16 Newton, and so that will be 13 Newton. So that will be 31.84 Newton. So thank you for watching my video, and I'll see you next time.